Hello everyone. In this video we are going to discuss the geometrical interpretation of vector product. By geometrical interpretation we actually will see in this video that how vector product can be obtained or can be used to find the area of a parallelogram formed by two adjacent sides of a parallelogram, which are actually the vectors, and we also see how the vector product can give us the area of the triangle also formed by two adjacent sides of the triangle. We will consider two vectors which are co-initial in both the cases. So let us see how it is done, and then we will also see in this video some of the examples where this vector product is used. So that is geometrical interpretation of vector product that we are going to discuss here. See, two vectors are considered here. One is vector A and another is vector B. You can see here we have shown both the vectors, vector A and vector B. The magnitude of vector A is given by OP and that of vector B is given by OQ. So these two vectors can be used to form a parallelogram which is given by OPRQ. So this is the parallelogram which we can see here. The angle between vector A and vector B is given by theta here. Now if we want to find the component of vector B along the y-axis, let me draw this y-axis. Suppose this is the y-axis which we are considering. So the component of vector B along this direction, we will drop a perpendicular here. We'll drop a perpendicular here which makes an angle of 90 degree. So from this point to this point, the length is obviously B sine theta. Okay. So this is the component of vector B along y-axis. So it means that this distance, which is NQ, where n is at n it is perpendicular to the vector A, so it is B sine theta. The same length here B sine theta, and the same length QN, which is also B sine theta, which is the component of vector B along y-axis. Now when we look at this parallelogram, you must be knowing that the area of a parallelogram is given by the base into the altitude or the height. Now in this parallelogram OPRQ, the base has a magnitude of vector A which is given by OP, and the height is given by Q1 which is B sine theta. So obviously the area of the parallelogram can be written as A is the magnitude of vector A into the height. A actually also represents the base of the parallelogram, and Q1 which is the height, which is B sine theta. So it can be written as B sine theta. So the area of the parallelogram will be given by AB sine theta, and we all know AB sine theta is the magnitude of vector A cross vector B, and the magnitude of vector A cross vector B is given by, we can write it in this form, as you can see here, vector A cross vector B, we have taken the magnitude, we have used the modulus sign. So this AB sine theta, or the modulus of vector A cross vector B, it gives the value of the area of the parallelogram formed by the two vectors, vector A and vector B. So I hope this is very clear to you. So therefore here it is also mentioned, which I have already discussed. We have the angle theta between vector A and vector B. We have dropped a perpendicular QN on OP. The magnitude of the vector product, which is vector A cross vector B, is given by AB sine theta, and this AB sine theta, AB is OP and B sine theta is QN. So which gives you the area of the parallelogram. Okay, so you can see here area of the parallelogram PQRS is actually the magnitude of vector A cross vector B. Okay, so I hope this is very clear to you. Now let us discuss this vector product of A and B in a bit different way in terms of a triangle. Now, to understand the concept of the triangle, suppose we have again considered the two vectors A and B, which are the two adjacent sides such that they are co-initial. Then we need to draw a triangle. Let it be starting from the point Q, and we have drawn a line. Please pardon me if the line is not straight, but the triangle which we are getting here is OPQ. Now, as we know, the area of the triangle is given by half into base, which is OP, which is the magnitude of vector A, into height, which is QN. QN is B sine theta. So half into AB sine theta, that means the area of the triangle formed by the two vectors A and B such that they are co-initial, then that area of the triangle can be given by half into magnitude of vector A cross vector B. I hope this is clear to you. So this is the magnitude which we are considering here. Now, when we have considered this, that means what we can say is it is half of the area of the parallelogram. The triangle area of the triangle is half of the area of the parallelogram, because AB sine theta or magnitude of A cross B represents the area of the parallelogram. So the area of the triangle is the half of the area of the parallelogram. Okay, so if you are clear, then we can write it in words. The magnitude of the vector product of two vectors is equal to the area of the parallelogram formed by the two vector as its adjacent side. That is for parallelogram that we have discussed. Now for a triangle, when we consider a triangle, then for a triangle what we can write here is, suppose A cross B we want to write here, so it is 2 into 1 by 2 of OP into QN, and OP is A, QN is B sine theta. So this is area of the triangle, half into OP into, this is area of the triangle. So vector A cross vector B, the magnitude is 2 times of the area of the triangle. So any way you can consider it, the triangle is half of the area of the parallelogram, or half of A cross B. That is A cross B, we are taking the magnitude only, or you can also write A cross B as 2 times of the area of the triangle. Okay, so I hope this is very clear to you. So therefore we can also write the magnitude of the vector product of two vectors, like A cross B, we are taking the magnitude, is equal to twice the area of the triangle formed by the two vector as its adjacent side. And you have to consider one thing, the adjacent side should be so that it has the same initial point. And that is these two vectors, vector A and B, are acting as a co-initial vector. So I think this whole thing is clear to you. If the two vectors are co-initial and they form a parallelogram, then their area will be given by half of the magnitude of their cross product, and the triangle which they forms is given by half of the area of the cross product. So if this is clear, then we will discuss a few examples of this cross product. Okay, some of the examples that we are discussing here is, the first is torque. Here you need to understand that when we consider torque, torque is the effect of force which makes a body to rotate. That means for the rotation of a body, torque is required. But torque will be obtained only when we apply force. So you need to understand that. Suppose we apply force on a body, the body moves in a straight line. That is the linear motion. But when we apply torque on a body, then the body rotates about in axis. A simple example is the closing and the opening of a door, which is bolted to a wall. Now when you close it or open it, you apply force. But the door doesn't have the linear motion, it has a rotational motion. That means the effect of force is rotation. So the quantity which we get, that is the effect of force, is known as torque. And the value of torque is given by R cross F, where R is the distance of the axis of rotation to the point where you are applying the force. Suppose you apply the force on a door, then the point where you apply the force and the distance of axis of rotation from where the door rotates, that distance is given by R, and F represents the force. Their cross product you take, that will give you the value of torque. So I hope this is clear. Now second example is angular momentum. Angular momentum is when we consider a body to be rotating about its axis, then many of the point of the body is rotating in a circular path, and it has both linear motion, which is shown along the tangent to the circular path, and a rotational motion also. Now when a body rotates about an axis, the momentum of the body is not the linear momentum. Along with the linear momentum, we will have angular momentum also when the body rotates, which is given by L. And there is a relation between linear momentum and angular momentum. Linear momentum is represented by P and the angular momentum is represented by L. So L is equal to R cross P. So this is the way in which a angular momentum is represented in the vector as a vector product of R and P. So these are the examples of vector product which are shown to you. Let us see another example. For instantaneous velocity. Now when a body is moving in a circular path, it has linear velocity, which is given by the direction of tangent to the circular path, and omega is the angular velocity because it is rotating about an axis also, which passes through the center. R is the radius. So there is a relation between linear and angular velocity. Linear velocity is angular velocity cross the radius vector. That is, the cross product of angular velocity and radius vector gives us the linear velocity. Okay, so these are the examples where we actually use the vector product. And these all topics will be discussed in the syllabus of your class later on. Now, before I conclude this video, let me tell you one very specific or similar feature between torque and angular momentum. Like for torque, we have written R cross F, where torque is in rotational motion and force represent the linear motion. Similarly, for angular momentum, we have P representing the linear motion and L represents the rotational motion. So these are the similarities which you can see here. And these three are just the examples. You will study in details in the later syllabus in this class only. So I hope everything is very clear to you. But still then, if there is any doubt, you can post me the doubt. Thank you.